Hello, calculus students, and welcome to another online lesson, perhaps the last online lesson of the year. Today we are going to learn about finding integrals using a technique known as substitution. It's a little bit like chain rule in reverse, but a little bit more advanced than that. And we're going to use that to find integrals of more complicated functions, ones that may have looked like they would have required something like the product rule if we were doing the derivative, but we are not. So I don't really have any terms and notations to start with. I'm just going to show you my technique. So because it's substitution, that means just like with chain rule when we first started out, we are going to actually substitute. But unlike chain rule, whereas as we got better at it, we had to show less and less work, when they get to these more complicated ones, we have to show work. Now, how do we know that we're going to use our substitution technique? You'll notice there are two functions here getting multiplied together. That is a sure sign tell that we have to use our substitution method, or at least it's an indicator that we may have to use it. And the fact that both of them have x's, both of those functions, that's even further rather than just undoing, say, chain rule. So again, it looks like product rule, and at least for this class, Mathematics SL, that's about as complicated as we're going to get. So again, substitution. Now, of those two functions that I sort of put in these little pans or bracket things, one of them is much more complicated. It is the x squared plus 1 because that then is being raised to the fourth power. So whatever the big picture is, and the big picture is we've got some stuff getting raised to the fourth power, that becomes your u. So we have u equals x squared plus 1. Then we're going to do the derivative of u in terms of x. And normally we just write u prime, but for today, I am going to write the full thing because you'll see in a moment it becomes a little bit helpful to show why this all works out. And the derivative of u in terms of x is 2x. Now I go back to my original integral. My original integral was some stuff to the fourth power, and I'm going to write that as u to the fourth power, all dx. Notice I've left some spaces. And then you'll also notice that there was a 2x in this problem. Well, lo and behold, my derivative of u in terms of x is equal to 2x. So instead of writing the 2x here, I'm going to do a direct substitution for this and replace it with du dx. I guess I didn't need all that space up front. So I have all this, which was my u. It's getting raised to the fourth power, and I wrote that right here. Then I had also getting multiplied by 2x, but I know that 2x is equal to the derivative of u in terms of x. So I wrote that down as a direct replacement as well. I have not done any integrals yet. Now, before I do the integral still, notice that multiplying fractions is easy. I can go straight across, and dx cancel out, so I just have du over 1, also known as just du. So now we're doing the integral of u to the fourth power in terms of u. And this is just an integral we can do, no problem. So let's do the integral. We take our exponent, we raise it up by 1, so it becomes the fifth power, but we also have to divide that new exponent or multiply by its reciprocal, so we have 1/5 u. And because there is no boundaries, we call this an indefinite integral or undefined, and we add on a c. But that's in terms of u, and our original problem wanted it in terms of x. So let's bring it over here, and we're going to replace. We have 1/5 times our u, which is x squared plus 1 to the fifth power plus c. And that's that. Now, if we wanted to check out to see if this actually worked correctly, we could now do our derivative. I'm going to do that in red. Always a good idea, especially when we're trying something new. So I have some stuff here being raised to the fifth power. So I'm going to bring the 5 out front. There was already a 1/5 there, so those cancel out. So now I have my stuff, x squared plus 1 to the fourth power. But I also have to remember to multiply the derivative of the stuff, which is 2x. My c is a constant. It goes away. And lo and behold, this is what we had when we started. And that is integration using substitution. Let's do one or two more. Once again, we see there are two parts to our function getting multiplied together. One of them slightly more complicated than the other, and that's usually a good indication it involves our u. So we have sine of x getting squared, so I'm going to let my u become sine of x. Then my derivative of u in terms of x is going to be cosine, remember it's derivative, so cosine of x. And yet, I think I did that wrong. So let's try this again. I was thinking of this as being the whole quantity squared as my original function, and yet it's not the whole thing being squared. It's just the x being squared. So I actually have my parts wrong. And I knew my parts were wrong because as soon as I got here, cosine x, that was nothing like what was left over. So we had some issues going on. So if it's not working out, it's a good telltale sign that something went a little bit wrong. So my u shouldn't be sine. My u should be what we're taking the sine of, and we are taking the sine of x squared. Then the derivative of that becomes 2x. Now you might say, well, I don't have a 2x either, but I've got something a lot closer to that. So far we're in good shape here. So let's rewrite our integral now using u's. So we have x, which I'm going to leave alone for a second, sine of x squared. Well, x squared was the same thing as u, so this is going to become the sine of u. And then we have our dx. But we still have this x here. And I don't have x over here, I have 2x. But could I get my x alone? Because I want to replace this x right here with something. So let's divide both sides by 2. Or another way to divide by 2 is multiply by the reciprocal of 1/2. So now we know that x equals 1/2 du dx. So I'm going to put my 1/2 here. I can put my du dx here as well. But what happens when I multiply this du dx times that dx? Well, these dx's cancel out, and I'll bring my du to the back. So now I have this nice integral of 1/2 sine of u du. And that's something that we can integrate. Remember, constants, we can just bring out front, not that it really matters. And then we take the integral of the sine of u, which becomes negative cosine of u plus c. And I double check. Sine derivative turns into cosine, but cosine turns into negative sine. I have a negative sine. Yes, so it all checks out. And now I need to plug back in my u's. So I have negative 1/2 cosine of my u, which was x squared plus c. To double check, let's do our derivative. So I have a constant. It just hangs out. I have cosine of some stuff, which turns into sine of that same exact stuff times the derivative of that stuff, which would be times 2x. Well, this 2 here and this 1/2 are all getting multiplied together, so they cancel out. I can bring the x out front, and so I have negative x sine of x squared. C is a constant, it cancels out, and that is what, almost what we started with, but I've got a negative. Did I do something wrong on my derivative here? I'm sorry. Sine of x, when I do my derivative, yes, cosine x right here. Cosine doesn't become sine, cosine becomes negative sine. And that's where my issue happened. So it was not in the actual work, it was just in my check. And so that will make this final one positive, and now we're good. All right, one last example. This one is even less obvious than the previous one. We have sine of x over cosine of x, but it's that over that's the key. It kind of looks like quotient rule if you look at it quickly here, but again, we're going the opposite direction, and it's the division. And what's being divided? Well, the thing that's being divided is the cosine of x, so we're going to let that be our u. So u equals cosine x du dx equals, and again, keep this straight, I think negative sine of x. Yep, I agree with that. And then we plug it all in. So now we have the integral of 1 over u. And then that was essentially getting multiplied by the sine of x, because again, you can think of this problem that we originally had as 1 over cosine x times sine of x. And then those would just become sine of x over cosine x. And we have our dx. So we still need to get rid of this sine of x. But we know that negative sine of x equals du dx. So I could just multiply both sides by a negative, which would make a positive sine x equal negative du dx. So I'm going to bring that negative out front, and I'm going to put my du dx right here. And again, that's all replacing sine of x, negative du dx. These cancel out, and now I have the integral negative, the integral 1 over u du. If you want me to rewrite that, it would look like such. And that is definitely something we can do the integral of. So we just bring down our negative sign, and that becomes natural log of u. Technically absolute values, but I don't think they'll take off points if we leave that off. So the natural log of u. And then we just bring back our substitution. So we have natural log of cosine x plus c. And again, we could check that. We have negative, and natural log of cosine becomes 1 over that stuff times the derivative of that stuff, and the derivative of cosine would be negative sine of x. The two negatives cancel out. We can write them right on top of each other, so that is sine of x over cosine of x, which is what we started with, and that worked out great. All right, we have some problems from the book that I would highly recommend taking a look at on page 467, number 1 through 5. Until next time,